much. Bom dia, todo mundo. Meu nome é Yoshio Isozaki. I'm a Director General of Marine Technology Engineering Center of JAMSTEC. I feel very honored to have been invited to this seminar. My throat is not so good condition, so please look at the screen more than that to listen to me. Okay. Today, I will explain the technology on underwater vehicle and manned research submersible in Japan. In Japan, it's similar to in JAMSTEC. Okay. At first, I will introduce our JAMSTEC briefly. JAMSTEC, Japan Agency for Marine Earth Science and Technology, is a leading institute for marine science and technology in Japan. It's founded more than 4 years ago. Then the employees about 1,000. Then our budget, annual budget is around 400 million US dollars. So around 1,400 scientists, 200 engineers. We have also the crew to operate our research vessels. Our JAMSTEC is, I feel confident. JAMSTEC is comparable with the famous institute such as IFREMER, Scripps, and USHOL. In future, probably INPO. Okay. We have two main sectors. One is research sector to carry out the research activity. And the one is the engineering center. Engineering sector to support the scientific activity through the engineering development or operation of our infrastructure, research vessel, manned submersible, research vessel, and the AUV or supercomputer. This is our main role of JAMSTEC. Research on global change or research on Earth evolution, research on biogenoscience, and technology development. Recently, research on seafloor mineral resources are highlighted. So such a department are organized in JAMSTEC. This is our research vessel in operation. We are now operating 8 vessels. This is a scientific drilling vessel, largest scientific drilling vessel in the world. Also, oldest one is around almost more than 30 years old. So this Shinseimar is completed last year. It's a world advanced science research vessel. So among 8 vessels, operation of 7 vessels are outsourcing to a private company. This, we, JAMSTEC, operating by ourselves, this Hakhomal. In addition to the 8 vessels, we are now constructing a new research vessel. It's larger than our fleet, approximately 100 meters long, and gross tonnage is 6,000 tons. It will be completed at the end of 2016, 2 years later. So main purpose of this vessel is to carry out the 3-dimensional seismic survey or sampling of the seafloor mineral resources and marine observation and survey. These are our typical submersible and underwater vehicles in operation. 10 years ago, this Shinkai 2000 is retired. Now we are operating Shinkai 6500. So we saw also operating the ROV and AUVs. This next, I would like to introduce manned research submerged Shinkai 6500. Now it's a famous in Brazil. Okay, this has a 9.5 meter long, and the total weight in air is around 28 tons. So as of today, Shinkai experienced around 4,000 dives. Shinkai means deep sea in Japan. So sometimes deep sea 6500. It's very simple. So later I'll show some movie. This is a photo taken in the Rio Grande last May. Okay, this is granite. This granite, origin of this granite is inland. So some media said Shinkai discovered historical Atlantis. So this is the survey on the seafloor. After the 3 years ago, we had a terrible accident, terrible disaster. At the time that we surveyed the seafloor. This is a history manned research submersible in Japan. In Japan, we started the operation of the manned research submersible around 80 years ago. This figure shows the operating depths. Then this is a year interval between two innovation. Not only the diving water depths, some of the observation system were improved. Then around 30 years, more than 30 years ago, Shinkai 2000 was completed. Then after the around 1,400 dives, she retired. Then such technology, these technology are integrated in this Shinkai 6500. Okay, this is our historical history of technology development in the manned submersible in Japan. You know, Shinkai already 9 years, but after the completion of Shinkai, 25 years passed. Then we have to transfer our technology to the next generation. So this is our history of the development of Shinkai 6500. We have, in Jamstick, we have a hyperbaric chamber. Maximum pressure is 147 megapascal. It means corresponding to the 15,000 meter water depths. And in using this hyperbaric chamber, we have tested. In this pressure hull of Shinkai is 2000 is a high tensile steel. We changed in Shinkai 6500. This is we used titanium alloy to confirm the reliability of titanium alloy. We carried out some extensive tests. Finally, we broken this model with this pressure, 13,200 meters. It's deeper than the deepest point in the world. Deepest point in the world is 10,911 meters. So if we drop in the deepest point in the world, this is not broken. It is the construction of the pressure hull. This is a sheet of titanium alloy. Thickness is 17.3 meters. Then pressed with a weight. Then we used hemisphere, like this. And it's cutted. And the two hemisphere welded into the one hull with the laser beam welding are used for this. To keep the reliability, we just welded one line like this, two hemispheres and welded on the one line. Then we completed the pressure hull. Inside diameter 2 meters. Tree viewport is provided here. Also, at the final test, in Japan, it is not available to carry out the pressure test, actual one. So this actual pressure hull transported to Japan, to United States. Using a Navy laboratory, we carry out the pressure test, then back to Japan. Also, various equipment, various systems are provided this bird cage. This bird cage settled inside of this pressure hull. This is a floating material. Then finally, Shinkai 6500 is completed around 25 years ago. Okay, last year we carried out round the world voyage called Kubere 2013. This is a Shinkai 65 and their mother vessel, its mother vessel Yokosuka. January, both started this round the world voyage, then go to the Indian Ocean, then carry out several diving, then go to the off Brazil, then around 16 dive were carried out off Brazil, then move to the Caribbean waters, then back to Japan in August and change the battery and go to the New Zealand. This is a Kermatic trench. We carried out Tonga trench and Kermatic trench. We carried out. During the Kubere 2013, we carried out 40 dives. Last year, in total, Shinkai carried out 55 dives. 55. Usually, they carried out 60 dives per year. Okay, this is some photo visited to the Shinkai visited to the Rio de Janeiro and Sao Paulo last year. A ceremony, welcome to the Shinkai to Brazil, was held on the 6th May. Janice-san here, okay? So also this is on board Yokosuka. Somebody BIPs visited to our Shinkai. So also the May 5th, I made some short presentation here. Anybody in this photo is here in this hall? No, only Janji-san. Also, I'll show some movie of Brazil. We carried out research called Leg 1 at Sao Paulo Ridge and Rio Grande Rise. Leg 2, Sao Paulo Plateau. Okay. Then Leg 1, we carried out 7 dives. And Leg 2, we are 9 dives. Leg 1 is in the Rio Grande Rise, around 100 meters deep. Then in Sao Paulo Ridge, 2,600 to 4,200. In Sao Paulo, around 300 meters. I'll show the movie for Leg 1, Sao Paulo, Rio Grande Rise, and the Sao Paulo Ridge. 2 minutes video. Shinkai now start diving. Some divers take us as video. This shows this San Paulo Ridge. From the sea bottom, some sample is recovered. Purpose of this visit diving is to find out some biological research. So many lives were found in the of Brazil. Okay, this is granite found in the Rio Grande Rise. So people say that this is proof of the historical Atlantis. Researcher found out that some bone of the whale in this of Brazil. Okay. I think to develop the new technology, new system is an important technology, but also to operate the such development system safely and effectively is another important technology. So I will show some operation technology. 3 years ago, in Japan, we had a terrible disaster in the northeast part in Japan. This is a huge tsunami. At the time, we are supported from the many people all over the world. I would like to say many thanks. So 3 months later, after the earthquake, Shinkai dived near the epicenter. This is just the epicenter of the heavy earthquake. Then the 3-point Shinkai dove. Then I'll show the site one, deepest one, around 5,400 meter water depth. So many cracks on the seafloor were found. Several years ago, Shinkai carried out diving at the same place. At that time, the complete flat area. But after the earthquake, Shinkai found so many cracks. Length of this crack could not identified. Next, we carried out survey of hydrothermal vent in the western part in Japan, around 1,500 meter water depth. This video was taken the ROV. It's a diving parallel with this Shinkai. Okay, thank you. you say some black smoker and white smoker were founded by the Shinkai. Okay. As I explained, Shinkai carried out an extensive survey. Also, she will carry out another survey. But 25 years passed since completion of the Shinkai 6500. So it is our responsibility to transfer the technology on manned research submersible. In Japan, as I explained, we have long history of the technology. So we wish to transfer to the next generation of these group. So now investigating such a new next generation submersible. It's a full depth, full vision submersible. Now we are just start the examination. Okay, then I introduced the technology on the AUV. This is Urashima, 10-meter long, and the weight of this Urashima is 10 tons. I think this is the largest AUV in the world. Now they carried out operation diving for 160. So this image was taken in the hydrothermal vent area by using the acoustic system provided on board this Urashima. Okay, this is a hydrothermal vent located here. So we took such acoustic image using the surface vessel. This is acoustic image taken from the surface vessel from the around 2,000 meters above the sea floor. Okay. Urashima can cruise just 100 meters or 80 meters above the sea floor. Then its Urashima can take a precise image near the sea floor. Also now, recently, we developed the new AUVs, cruising AUV, Jinbei, cruising AUV, Yumeiruka, and working AUV, Otohime. Such sometimes acoustic image will be taken by the AUV, but now we are trying to take a photo image using a 3D laser scanner like this. Also, this cruising AUV Jinbei takes the image just near the Japan Sea, like this. Methane hydrate plume, methane hydrate area like this. We identify the area. This is a reach of the methane hydrate. So also in case you may look, okay, usually AUV cruising the sea bottom to cruise over such a rock or mountain, like AUV like this, head up and down. But in this Yumeiruka, four controllable fins provide in front, also in rear, 4 controllable fins are provided. So then cruise like this, keeping the horizontal. It's a new technology. To develop this setup, also to develop such a AUV, we develop elemental technology. Okay, this is ring laser gyro, INS. You know that in the underwater sea, we cannot use the GPS to find out the position, to find out the location. Instead of the GPS, we have to use the INS, inertial navigation system. So this INS was developed by the Jamstick in collaboration with a Japanese manufacturer. Detail I'll show you later. Also, we are trying acoustic image transmission system. Also, we are challenging the long-distance acoustic communication system. This shows a 600 kilometer, but later we succeeded 1,000 kilometer communication. So also this is a high efficiency fuel cell system used in the underwater vehicle. Okay, also this is a micro COT pH hybrid sensor. All these elementary technologies were developed and incorporated into our new AUVs. This is just a comparison table of INS. Famous INS manufacturer is Fins in France. This is a newly developed one. Compare with the size, it is very compact and the weight is. This INS is an old generation, is provided on the Urashima. Now we developed a new one, very compact. So accuracy is similar to the world-class INS. So I can say it. We have developed a very compact INS with having an accuracy level, having the same accuracy level with the world-class level. Okay. Next, I introduce our remote operated vehicle, ROV technology. Now we are operating the hyperdolphin and Kaiko. In case of a hyperdolphin, maximum water depth is 3,000 meters, and some attachment is replaced in that 4,500 meters. Already, we carried out more than 1,600 dives using this hyperdolphin. Also, this Kaiko 7,000 can deep to the 7,000 meters, and already 600 dives is already carried out. This is a small ROV, we call it Abysmo. Just our engineer developed this whole by downsamples. The maximum operating depths are more than 10,000 meters. This Abysmo recovered the soil, the sample from the bottom of the Challenger Deep. Okay, now we developed a new heavy-duty ROVs. This ROV is just a vehicle. We call this operation to this Kaiko system. This is a launcher. Launcher down to around 7,000 meters. This vehicle deploy from this launcher. Then this vehicle can operate freely from the launcher. Then this Kaiko Mark IV, called Mark IV, is a replacement of the Kaiko vehicle. Then this is have a larger payload, 3,000 kilograms. Then powerful thruster. Also, this ROV can operate like an AUV using an autonomous navigation system. This is the original cruising route. This ROV actually can follow this actual link. In the world, there are, according to our investigation, in the world, there are 6 ROVs for scientific research, and deeper than the 6,000 meters. There are 6. So among 6, now Jamstack are operating 3. Okay. The Jamstack activity is focusing to the deep sea research. As I said, payload Other vessel, other ROV has a payload less than the 200 kilogram. But in new ROV can handle the 300 kilogram payload. In near future, now we are developing to adapt the coring system, boring system to this Kaiko Mark IV. Just at this moment, such ROV can pick up such sample from the, but this Kaiko can drill such a boring system. Then it can recover the hard rock in near future. I show that typical of our technology development. One is acoustic image transmission system. Now, Shinkai 6500 have provided this acoustic system. This is an image taken by Shinkai, and this photo transferred to the mother vessel using the acoustic system. This is a received image on the vessel. Okay, you can identify such a image in the seafloor, but transmission rate is 1 image by second. In case of Urashima, now we can transfer image 1 image per 4 seconds. It's dependent on the resolution. It's precise resolution at the time the 1 image per 8 seconds. Now we are developing a new system to transfer such acoustic image 1 image per second. 1 image 1 second. 1 image 1 second. Almost similar to the animation. Now we are trying. Next, the high efficiency fuel cell system. This fuel cell system is a high efficiency and reliable energy source. In the laboratory, we succeeded continuous operation of 6,600 hours. This is the old one provided on the Urashima, old AUV. Now we succeeded, completed new fuel cell system. You know, this the weight is 1/4 the self-consumption power. Some fuel system consume such system consume the energy. So if we reduce the self-consumption power, output are increased from this fuel cell system. So this fuel cell system will be used as a power of the AUV, and in addition to that, we are now considering to the station or the observation station, fixed observation station in the seafloor at that time as energy source. We can use this fuel cell system. We are now challenging the observation and the survey in deeper and harsher environment. Okay, like this. This is the new developed OBS, usual OBS, ocean bottom seismograph. In case conventional OBS can operate down to the 6,000 meter, but this OBS can operate in the 11,000 meter. You know, in Japan, the Japan Trench, water depth of Japan Trench is around 1,000 meter. To survey the earthquake, we need this deeper OBS. This OBS, usually conventional OBS, is a pressure hull made of glass. But in case of the ceramics, also we now developing that autonomous flying shuttle instead of the permanent V. So also we just developed, the Argo. It's a famous observation system all over the world. Instead of Argo, now existing Argo can dive around 2,000 meters. But to monitor the Earth environment, we need to survey deeper than 2,000 meters. So now we developed a new deep water profiling system to dive the 4,000 meters. In near future, now we wish to realize such an integrated four-dimensional ocean survey and observation system integrating our all technology like this. Using full depth submersible, new ROV, some monitoring system, some sea bottom monitoring system to monitor the earthquake. Or AUV can operate independently from the research vessel. Also, our constructing a new research vessel can do like a three-dimensional multi-channel seismic survey. Okay. This is our future vision. Muito obrigado.